It's my pleasure to welcome Pérola Milman to open this session, and she's going to be talking about GKP coming out of the box. So thank you very much.
Hello, thank you for giving me the opportunity of sharing this work with you. I'd like to tell you that's pretty weird for me to talk in these conditions. I'd rather be clustering with you somewhere, but unfortunately it's not possible. So I'm going to talk to you about today about this joint work with involving several people, and both theory and a little bit of experiment. So my title has a triple meaning that I hope will become clear during the talk. One of them is a joke, the other is quite pretentious, and the final one is physical. So this work can be found in PRA and in arXiv. Okay, so well, usually when you talk about quantum continuous variables and bosonic codes, we mean X and P variables, momentum and position, or something that is equivalent to that. And this can be expressed in terms of creation and annihilation operators. So in this sense, there are some important elements, both for physics and computation, that is, for instance, photon statistics, and in particular, Gaussianity and non-Gaussianity, that is related to the usefulness of such states for some quantum tasks. And this is something that can be pictured in phase space using distributions, as for instance, the Wigner function that's shown here for these two states, which are quite different from the point of view of Gaussianity and non-Gaussianity. Okay, so experimentally, well, I'm in the context of quantum optics. This is where I come from. There's continuous variables. So, well, they have been discussed in this conference. They can be encoded in vibrational modes of trapped ions, and the quadratures of one mode of the radiation field that can be either inside or outside a cavity. And using this kind of quantum optical system, which are relatively intense fields in one mode, well, they display some advantages, as for instance, we can generate quantum states in a deterministic way. And you can also reach high measurement efficiencies using homodyne detection or something that's equivalent to that. But there is also some disadvantages, as mode isolation and preparing non-Gaussian states, because this involves some photon detection, photon extraction or addition. And then by doing so, we use one of the advantages, which is determinism. Okay, so the idea here is about using quantum optics still, but different continuous variables in quantum optics, sorry. So those are the continuous variables associated to single photons, as for instance, time, position, and frequency. So how does it work? I'm going to anticipate here some criticism, which is not very pedagogical, but I'm doing so because I use it to such criticisms. So usually when we think about using single photons for quantum information tasks, we think about qubits that can be encoded in the polarization of photons, which are binary variables. Also, there are some applications involving qubits or orbital angular that can be encoded, for instance, using the orbital angular momentum of photons. But here, what you're doing is something else. We'd like to use continuous degrees of freedom of a single photon. And like to recall that the quantum aspect of all these quantities that are also defined for classical fields, it's in the single photon nature of the photons, the commutation relations of the photons. So there is no, this is the quantum aspect of the thing. And we're going to see this in more detail. Okay. So you can also say that using single photons for quantum information application is not very interesting, because you can have problems with scalability and also for in creating quantum states, generating this single photons, and also detection efficiency, and the photons cannot interact. Okay, but the point is that, as I mentioned before, doing something that is, well, doing interesting things with intense fields also involves creating non-Gaussian states, and then you lose some of the advantages of intense fields, and you have this kind of problems as well. And actually, the idea here is not, well, I'm a physicist, so we can discuss about advantages and disadvantages, but I'm doing this, well, the motivation is curiosity. So the idea is to find out if we can create an analogy between having one photon in many modes, continuous modes, and one mode of the radiation field with many photons. Okay, so what's the box, the physical box that appears in the title? So this box is, it's an experimental system that we study in the group of Saraducci, that is a collaborator, and it's my team as well. So this is a nonlinear system where that can be pumped by an intense field. And then this is a semiconducting structure with a nonlinear, where nonlinear interaction takes place. And then one photon of the pump is converted, can be converted into two photons that we call signal and idler, these small letters S and Y. And this box has an index of refraction that is different from the air. So it works as a cavity. And this is why when the signal and idler photons get out of this cavity, they have this periodic structure here because they bounce back and forth inside the cavity. Here on the right, we have a picture of this box that looks a little bit like a Kit Kat. So when these photons get out of the cavity, these photon pairs, they can be detected in coincidence. And we obtain what we call this joint spectral intensity. That's going to be very important in this talk, which is the intensity of the number of photons detected in coincidence. Okay, so when you do this, we find this kind of picture here on the left. So this is the joint spectral intensity as a function of this signal and idler photons wavelength. So find this periodic structure here that shows that there is some correlation between these two photons. And what we have here actually is, well, this work came from this picture. We saw this picture and we asked ourselves, is there a sense on talking about GKP states from this picture or not? Is this a picture of a GKP or is this a true GKP? So this is a kind of artistic question that's analogous to the one that Magritte raised with his famous painting. Okay, so the idea is to see whether we can find a GKP in this picture. And there are many issues to be addressed. One of them is that, as I mentioned, we have only two photons, which are signal and idler, that are entangled. We don't have intense field. Well, I have to define phase space for this. Can we do this? And find out what's quantum about this. Okay, so to answer to these questions, we'll have to identify the tools, the mathematical tools that will enable us to answer to this point. So omega here is the frequency of mode. It defines a mode. So, and we have associated creation and annihilation operators. And they do not commute unless they have different frequencies. So this is what's going to replace in this work, this X and P commutation relations. So for us here, a state is defined in the following way. Whenever we create one photon at a given frequency, we call it omega. And this is analogous to what we call X or P in the usual description. So one single photon state is this wave function here. That's a function of omega here on the right. I don't have my arrows, so that's not the problem. So this is our state, a general state. And then we can also define, of course, this creation and annihilation operators in time. That is simply this Fourier transform of the operators in frequency. Time here, the physical meaning of this is some kind of position or time of arrival of a single photon in the detector. Okay, by combining these operators, we can create also displacement operators. You see that we annihilate photons at frequency omega and create it in a displaced frequency, and the same for time. And then we recover as well this Y relation. So there is a sense I'm talking about phase space here. We can define it and we can show that frequency is the generator of time displacements and vice versa. Okay, so from this, we can also mathematically define what we're going to call, what we could call this GKP states in frequency. So there's 0 and 1 here, for instance. And if you create time, for instance, time displacements of some fixed quantity, then you can show that there are eigenstates of this operator. You do the same thing and define X operators as well. So they look like this. This is an infinite superposition of infinitely squeezed states, as usual. I think that everyone here is knows that very well. And just to fix the notation, well, we can also define physical states, which are, so we start with the ideal state, say, and then we have some displacements in time and frequency with a given distribution that we consider here as being a Gaussian distribution. And then the physical GKP states looks like this. We can describe this kind of object using these operators that we just defined. Okay, let's move back to physics. We have our box here, and we introduce some new variables. So what goes out of the box? I'm going to change variables and use the sum of frequency of signal and either photons and the difference of the frequencies. And then we know, physicists, that, well, the state that goes out of this box is given by this wave function that involves both omega minus and omega plus, and then the signal and idlers frequencies that can be written like this. The goal here is to find out how this wave function looks like, which can be done by other experiments and simulating the system. But we also have theoretical models that I'm going to show you now. So the idea is the following. This wave function can be written as a product of omega plus and omega minus functions. And then you have these frequencies that represent the effect of the cavity that depend on the signal and idler functions as well. So this first part is just a product of two Gaussians. One of them is simply the pump, and it's a consequence of energy conservation of the photon of the pump that gives rise to two photons, the signal and the idler. And the other is essentially the Fourier transform of the overlap between the pump and the medium. It's related to momentum conservation of the photon that creates the pair of photons. But here we will consider that the width of the pump is much smaller than the width of the Fourier transform, and then so we can approximate this pump by a delta function. It makes our life easier. So for the cavity, well, it's a sum of it's a periodic function, so it's a sum of peaks of Gaussian functions that are far apart of what we call here omega bar, this frequency omega bar, and it's related to this tau RT, which is the time a photon takes to bounce back and forth inside a cavity. So everything is quite simple and natural. And these peaks, they have a small width, delta omega. Okay, so we have already defined our Gaussian distributions, and what we can show, making some manipulations in the tools that we developed, is that the state that gets out of the box is like this. So it's as if we have started with ideal GKP states, sums of 0 and 1s, and the GSI is thus this kind of chessboard of infinitely squeezed states that are signal and idler. And then we can suppose that we have operated on this using this frequency displacement operators that kind of enlarged this ideal states. And then finally, this time operators, they squeezed the distribution and created what we have seen in the pictures, the GSI, the experimental signal that we have seen in the pictures. Okay, so, but it's not over. We can also make some manipulations. We can look at this in another way. So this is our state, and just change notation and use the time basis. And so we can think about this as a circuit, a small circuit, where qubit A is signal, qubit B is the idler, and then they have some noise in frequency. This is the red part. And then in order to describe this collective displacement operator here, well, just have to recall that is a kind of C0 gate, an entangling gate between time. And this can be described in a circuit like this sandwich of time displacement operators and this entangling gate. So the whole thing that gets out of the box can be described using this circuit. Why is it interesting? Well, this is interesting because, as it has been mentioned here, well, we can show that this circuit is also a circuit that is a small cluster for measurement-based operations and error correction. So, well, this is some annoying manipulation, but as I think that most of you are aware of, this works exactly as a measurement-based quantum error correction. So whenever we detect one of the states in time, for instance, you can do the analogous of a teleportation, and then the other qubit A here, inherits of the noise properties of qubit B that has been measured. So this allows for correcting qubit A. So the conclusion of this part is that the state that is naturally produced from this box is a small quantum circuit that's useful for quantum error correction in the context of measurement-based quantum computing. Okay, but we can do a little bit more. We can take these photons that get out of this cavity and send them through an interferometer before detecting them in coincidence. This is the Hong-Gomando interferometer, and the main ingredients of this are the following. So in this first part, you can create time displacements, a time delay between signal and idler photons, between the two photons. And then you mix them up in a beam splitter, and you detect them in coincidence in detectors A and B. So when you do so, we have shown this some years ago. This coincidence detector is equivalent to measuring one part of the Wigner function of this collective state. So this provides you with some useful, relevant information about the state. Moreover, you can see this time displacement exactly as a quantum gate that is being applied to one of the photons, here the signal. So if you fix well the time displacement to half the time a photon takes to bounce back and forth in the cavity, then you see that this is equivalent to a Z gate that's acting on our GKP qubit. So it displaces the qubit. So the experiment we have done, the experiment, and we have shown that this is the coincidence detection of the photon pairs. On the horizontal axis, we have the time delay. And in the vertical axis, we have the coincidence accounts of the photon pairs. What we see here, sorry?
Interrupt, is 5 minutes or 10 minutes total and 5 minutes till question time, but you can use that.
Okay, we can conclude in, I have only one more slide. And so what we see here is that, well, visibility is very low, but it's enough. We have shown that it's enough to show that if you see the time axis, actually it's displaced. On the left, it's displaced with respect to the right. The 0 on the right is the displaced, it's displaced with respect to the right. So this shows that this displacement really took place. Okay, so I will move to the conclusions. So I hope to have convinced you that it's possible, to build an analogy between quantum optical systems where you have many modes in one photon, the ones we studied here, and many photons in one mode. So this is a kind of different way of looking at GKP. This is why I call it out of the box, and this is the pretentious interpretation. So I showed you that spontaneous parametric down conversion, so this nonlinear interaction, is capable of creating naturally entangled GKP states that are useful for measurement-based quantum computing, at least in this very small scale. And of course, there are many issues to be discussed, as a scaling of this system and improving measurement efficiencies and the visibility of the curves that I showed. So that's all. Thank you. Thanks a lot. And I can ask questions if you have.
Well, thank you so much for the talk. Maybe everyone can put up a reaction or something. Yeah, there we go. Yeah, I think this was really fascinating. So again, if you have questions, just type them into the chat box down there and I can ask them if you don't feel comfortable unmuting yourself and asking the question yourself. And so I guess maybe I'll just start to make sure I understand. So the sort of Fox-based structure is that of like a photon, but the way you're thinking about it is the sort of temporal and spectral degree of freedom has this comb-like structure. So it's really analogous to GKP. Am I correct in that?
Yes, that's it. That's it. That's it. I mean, you can recover the main point is that you can recover the commutation relations between the relevant operators in this context, and you find a phase space as well. Well, there are some issues on the interpretation, so because the notion of squeezing is not exactly the same in things like this.
Right.
But this is the point, yes.
Yeah, look, it's really fascinating. So Julia is asking, do you have sort of continuation plans? Like, what's the research direction? And I guess you don't have to give away secrets, but yeah.
Yes. Well, from the experimental point of view, is improving the visibility, and from the theory point of view, there are some issues on improving this analogy to other tasks in quantum computing. That there are some points that are not very clear for us, involving, for instance, how to define other kinds of operators, not only displacement operators, but how exactly all this math would work.
Right. So Alec has a question. So does this mean that any coherent frequency comb can be thought of as a GKP state, or is there something special about this setup or this device?
Yeah, what's special about this device is that it has a single photon. Only this is very important because in this commutation relations and all this that I showed, especially the while one, as what it's relevant here is that and also defining like the equivalent to time and to X and P operators in time and frequency. What we use is that we restrict ourselves to the 0 and 1 photon subspace. So you cannot have two excitations. So this is why some part of the commutators, they disappear naturally, and then they reproduce what we know for X and P.
Yeah, I mean, that seems like the really interesting and novel part of what you do. But if I understand Alex's question, oh, he said that makes sense. I guess I was sort of wondering, like, you know, you could imagine that you have, if you just think of the longitudinal wave function, you have a 1D field, then the kind of analogous thing would be the multimode squeezed, like a multimode squeeze state with this sort of frequency comb structure. But I guess that's not what he was thinking about. Julia is asking which kind of errors can be corrected. Do you have an idea? And sort of related to that, Jonathan Home is asking, like, does the use of a single photon make this a fragile scheme?
Oh yes, of course. Well, first, yeah, first question is the kind of, they were related, of course, these two questions. And well, yeah. the errors that can be corrected is like frequency displacements, frequency and time displacements, of course.
Yeah. Okay.
And that can occur in a fiber or things like this. And the other question is, well, is of course it's if you lose the photon, all the information is lost. So this is one point that.
I imagine with that kind of thing, you might hope to do the kind of tricks that are done in KLM style optical quantum computing.
Yeah, this is an interesting direction. Yes, yes, indeed. This is an interesting direction. Yes.
Yeah.
Yes. We should try to match the two things. And also there's something else that, well, the PhD student that was involved in this project, Nicolas Fabre, he's studying this. It's kind of making some kind of phase space description that would match the two worlds. The world of single photons and the modes, and the world of intense fields and in a single mode. So kind of making a global phase space description and the description of states and combining these two things together. So he has some results that have been published, I think, in PRA. And I think this could be also interesting. I mean, the question would be, can one view help the other in some way or not? Right.
Yeah, it's one of the features of photons is there's so many degrees of freedom. So I'm sure there's so many games you can play with, you know, then thinking about polarization modes in addition and so on.
Yeah, because whenever you have a single photon, well, this is what happens. You there are some tricks that you can do, for instance, coupling different degrees of freedom of a single photon, and then do interesting things. I don't know, measuring the 4 Bell states and things like this. So this is the idea behind trying to match these two worlds. So can you, I don't know, teleport some frequency properties to the photon statistics or something like this? I know I'm just dreaming, but this is the idea behind his work.
Yeah, look, this is a fascinating talk, and so maybe everyone can raise their Slack emojis and thank Pérola again. So
I don't have access to Slack, but I thank you.